Good afternoon. Welcome to the concluding session of the Healthcare and Life Sciences track at TC16. I'm personally very proud of every session that has been presented, and I hope you've seen value from them. But of course, we reserve some of the best for the last. Precision medicine and genomics obviously is top of mind, and very honored to have Aaron Black, who's the Director of Bioinformatics from the Inova Translation Medicine Institute, present this session. I'm Andy Day. I'm the Global Industry Director for Healthcare and Life Sciences at Tableau. What that means is I run the innovation, go-to-market, partner ecosystem, biz dev for provider, payer, pharma, and med devices. So thanks to my colleague, Scott, I got to know Aaron sometime last year, and it's been an amazing collaboration. I'm very honored to call him my friend. Mm-hmm. We actually started this year with a bang, right? In the first week of January, we were both participating and speaking in a panel discussion on genomics and precision medicine at CES in Las Vegas, which is the largest consumer electronics show in the world, in the digital health panel. And since then, we have done a bunch of interviews together. It's culminated in some very compelling articles in Search, Health IT, Health Data Management, and others. I put them up on Twitter, on Data16. So if you guys are on Twitter, you can check it out. If you just Google, Inova Translational Medicine Institute and Tableau, you should come upon those. So with great honor and pride and pleasure, it's my, privilege to present Aaron Black from Inova Translation Medicine Institute to talk about personalized medicine, genomics, and precision medicine. Please take it away.
Thanks, Andy. I appreciate that, and I'm coming over a little bit of a cold, so thanks, Scott, for getting me this. Now that I talk out loud. I came to Austin thinking that the weather was going to kind of clear me up, and I came in from London, which was actually not rainy and actually sunny, so kind of balanced myself out there. But I'm truly humbled to be here because Tableau has been a great partner, and really I want to highlight two things in this presentation and even in this title. One is enabling. So what we're trying to do is find technologies that enable us. And there's no lack of technology. Many people know you've probably been pitched many things. So we're trying to find true partnerships, which is why we love to come to these meetings and meet other people that are actually using this in a way that we never would have thought of. Secondly, healthcare. So we do a lot of research within Inova, but we do in the spirit and underneath, I would say, the umbrella of healthcare. So we're not a true research institute. We're actually, our goals, and we'll go through that a little bit, is to actually apply this in healthcare. So there's some challenges there, there's some opportunities there for those of you who are in a healthcare system and trying to implement new technology. So today, really quickly, I'll go over this in a second, just a little bit about us, who we are, both Inova, the health system, as well as the Translational Medicine Institute where I work. Really go over why we and Inova believes in investing in translational medicine, and then look at the data journey, and I'm going to show you this the way we've used Tableau. We've used it in a wide array of applications. Then also look at the data infrastructure. So there's a lot of big data, messy data. I mean, whatever data, we're data people. We've had to build a pretty different infrastructure that was an evolution, and you'll see that through, again, some of the Tableau visualizations today. And then look at what we consider opportunities. There's a lot of challenges, but we also see a lot of opportunities. What we think is next for us, and then just the results of what we found and maybe some lessons learned that you can take back as you venture back to your home. So with Inova, we're a nonprofit. We're a community-based healthcare system. We're located in Northern Virginia. Our main hospital is in Fairfax, Virginia, so it's about 15 miles outside of Washington, D.C. Not so sure I want to go home this weekend. But we're a pretty big health system, and it's grown quite a bit over the last 10 to 15 years. I've been at Inova for 3 years now. I came from Columbus, Ohio, at Nationwide Children's Hospital, and came here, and they had a broad vision of what they wanted to do, which is become a global leader in genomics. And even recently, they've expanded their kind of footprint in this area. They purchased a facility that used to be the world headquarters for ExxonMobil, right across the street. And they're branding it the Inova Center for Personalized Health. And they're starting to do collaborative work with different institutions across Virginia. And actually, it's written into the government law that they're now matching dollars, the government, Inova, and an academic institution at a clip of about $112 million a year. for infrastructure, for recruiting. So this is a big investment for not only Inova, but for the state of Virginia. And it's humbling to be part of that because as you see the evolution, it didn't start that way. As you look at our institute though, at ITMI, we started around 2011. Our CEO is Dr. John Niederhuber, who was, before he came to Inova, was the director of the National Cancer Institute, or NCI. He started the Cancer Genome Atlas Project, which is kind of how I made my way over because I was part of that project. And what they've done here is really done a bigger version of that. So right now we're about 100 FTEs. I've been doing a lot of budgeting recently, so that will go up. But we're about a third clinical, a third IT and informatics and bioinformatics, and a third laboratory. So we have an integrated laboratory that does a lot of the sequencing, or at least the prep for the sequencing. So again, the goal of this institute is to apply this to healthcare within Inova, and hopefully beyond that. So we've been involved, again, for about 6 years in studies. So this is on the research side. So just to give you, we're all data people. We support over 12 studies, but most of them, 90% of our data is around preterm birth, the birth of a baby. So we actually not only sequence the baby, but we sequence the mother and the father. So we call that a trio, and in order to be enrolled in our studies ongoing, because these are our biggest one, our longitudinal studies following these kids over 18 years, we need to have all those individuals there. Another thing about us, again, integrated laboratory, we blood, saliva, urine, placenta. We've just got into microbiome, so we just are really just kind of latching on to that study because our patients come to us looking for these types of studies. So over the past 5 years, we've amassed a lot of samples, a lot of data, which really is a segue into why did Inova do this? And I have a couple slides because everybody's seen the why do this in healthcare slides. Mine's a little bit different. So I saw this is a Institute of Medicine study. It was actually in, I think, 2013, where they ranked the United States against all other countries in the world. But they didn't do it against, actually not all countries in the world. They really concentrated on countries that had the same resources that we do. So we didn't want to look at just, hey, we're always going to be at the top because we're the richest, one of the richest countries. They wanted to look at the other 17 countries that were most like us. And in this graph across the rank is, if it's higher, it means it's better. If it's lower, it means it's worse. And then across the bottom is the age, and this is mortality rates for men and women as they age. And what you can see here is the US, for the first pretty much 65 years, is the worst in the world when we look at this. But then when you get to 65, magically we become the best. So the key here is that the United States is really good at keeping you alive. But we're not so good at keeping you healthy as we move through. So a lot of the work that we're doing is to try to be more proactive, is to predict, to treat you more proactively as you come into the health system. And the other reason that I think Inova's been attracted to this is that consumers are demanding this. I mean, as you guys are probably immersed with different things, I mean, these are more academic papers, but think 23andMe, think Ancestry.com, think a lot of the ways that you're being, this is being promoted to you as, how can you learn more about yourself at a very personal level. So Inova is really saying, okay, we have a need here in healthcare to be more proactive and predictive, and we have a consumer demand for those types of services. So it's been kind of a blending of two different environments, and Inova is, again, taking advantage of those. But the reality is, and if you look at some of these things here, it's not exactly magic. And really, when you try to build these programs, and some of you are probably from academic institutions, it's really expensive. Sequencing, no matter what you've seen on the cost curve of it, went from $3 billion to now around 1,000. If you're going to do that at a health system level, that's still hundreds of millions of dollars. And that's just to generate it. That's not to do anything with it. So it's still expensive to do this. Also, when you look at the technology and everything, healthcare systems are pretty risk averse. They don't want to build big things that are going to break. They want you to prove to them that this is going to be viable and that it's number one, from a technology standpoint, also from a return on investment, this is something that you truly want to do. Talent. I mean, I don't know how many, there's probably a lot of talented people in here, and I'm always looking for talent. But it's very hard to find people that can deal with this data, both when you consider the subject matter expertise of people who do biology, clinical data, think about all the new technologies coming at us with cloud and big data systems. I mean, this is a really tight area, and a lot of times we're not competing with hospital systems. We're competing with, in DC, Oracles and Googles and Facebooks for that type of talent. So it's a very, very interesting area, but a very hard area to get a handle on. Data standards, whatever you've heard about electronic health records, and many of you are probably fighting this fight, it's still pretty immature. And I'm coming from the outside. I'm a research person, and I see the data coming in and going, what is this? It's immature. I mean, electronic health records are still pretty immature. And they're not built for research. They're built for billing. They're built for, am I going to get paid? Am I going to be able to get my reporting to the government so that I can get my Medicaid reimbursement? That's how they're kind of set up right now. And so there's a lot of work that we're doing to facilitate, hopefully getting better standards around that. And then overall, I think that a lot of times we get into unrealistic expectations. You hear all kinds of things from, whether it's companies, big data companies that'll say, hey, we can do this and this, with a bunch of buzzwords. A lot of times that isn't really reality because the data isn't good enough to just throw into a machine learning algorithm and spit something out. There's a lot of work that has to be done in order for it to get there, and that's what we're going to go through today. So with that context, the way I'm going to frame the rest of this presentation is, we're data manufacturers. I mean, we are taking data and moving it around this paradigm step by step. So understanding what the business wants, preparing it for the business, making it actionable, evaluating, is this something that you want? And then at the very end is when you deploy it. And right now, about 80% of what we do, and there's been a lot of research on this, is just preparing that data for someone to do something with. And that last point is about only 20% where we actually do the analytics. So what we want to be able to do is flip that. We want to get to the point where we're doing 20% of the work is the data preparation, and 80% of this is analytics. Now, this is a cookie cutter type of slide, but when you try to pitch this to leadership, they want to see visuals. But this is the goal. Now, I'm not saying we're probably, hopefully in the middle of the spectrum, but that's our goal, and that's how we promote our teams. This is why you need to invest in us, because eventually you're getting sold the analytics. You're getting sold the Watsons and the whatever. What they're going to do is they're going to sell you that, and the data's not going to be good enough, and they're going to put a bunch of consultants out there just to get you to get here. And I've had 4 or 5 conversations with that. So that's my venting for the day. So what that means right now is we have a translational journey, right? So this has not been something that, so Dr. Needy here, I love him to death, but he didn't come in here thinking we had to build this hybrid cloud environment with Hadoop and Tableau and all this stuff on top of it. He was on the science side. What happened was 2 years later, after they started to build this, they hired me and said, here it is. And this is a journey. So the first thing we had to do was look at what is the model behind this? What are you really capturing? And what this is my representation of a patient-centric data, what I call a logical model. And I'm going to jump out of this and see if I get into my computer at work. Because it's interactive. So you don't build that in a day. And I had come from TCGA, where the Cancer Genome Atlas was government-funded biospecimen repositories. Actually, maybe I don't have to do this. It might be in this one. Let's see if I can do this right. Yeah, it's small though. And we had already built a model to do it for cancer. And if you're in cancer, cancer is even more immature when it comes to data standards. And when you're doing cancers across 25 to 30 different cancers, they're all different, and everybody has their opinion. And so it was constantly changing. So they thought they wanted to answer these 100 questions, but then they saw the first 100 people answer it and go, oh no, that's not what I wanted to ask. And they change it. So you become this report and data munging team that's very hard to maintain when, again, the 80% actually became more. And you're spending so much time on 5% of the data and not the rest of it that it became cumbersome. So the model we built was to be more metadata driven. And what I mean by that is it's not so wide, it's narrow, and so we have the ingestion's faster. And I'll show you some examples of that. And let me see if I can blow this up a little bit so you can see it. Yeah, it was at 50%. All right, so this is our internal wiki page. So again, we have to promote this to not just me and our architects, but to the people who are going to use it. So we started with participant. Now I'm going to go to a case report form because that's the way that I'll show a lot of this today. Is we then said, okay, here's our kind of our area. How are we going to start to model this data? So we're very person-centric. So our patients come in, and they could be in multiple studies, so they're subjects, but they could be more than one. And so what we found is if we knew a lot about that person at the time we collected the data, it was wide. So we know everything about the person, their date of birth, the race, ethnicity, those types of things. So we kept that wide. But for things that we weren't sure, were they going to ask us now and in the future, we made them very narrow, meaning very metadata driven. I asked this question, I got this answer. I asked this question. We harmonize what they ask, but we have no idea how many times they're going to ask it, at what interval are they going to change what they call it. Medical, again, you could go to someplace in California, they would call exactly the same thing something different than we do. So we had to be able to be very agile the way we collected the data and then also blended it at the end. So that was just kind of the methodology, and I'll go back to the PowerPoint presentation. So at least you have a little bit of context there. So we did that for every single one. So we went through, and before we started even building things, we started to evaluate that, but we needed some way to see it, right? So some of this data is the databases, Postgres, Oracle, some of it's flat files, some of it is genomics, which is basically semi-structured text in what they call a variant file. So we wanted to visualize that. So what we started to do is literally put our data into Tableau and said, hey, what can we do with it? And we were actually, I think we had done a 60-day POC, and this is the first one I did because a lot of the things that we found about our cohorts is if you're in DC or in the surrounding suburbs is that you have a lot of people coming from all over the world, and they didn't know that, right? They thought, hey, we're a suburb we're in Fairfax, very much a demographic, but what ended up happening was we started to see people from all over the world coming. And this is not where their parents were from. This is where they were actually born, which is a key component. So what we did was we said, oh my, we got obviously a lot in the US, and babies, of course, all are going to land here. That's why that's even bigger than you think. But we're about 50-50, 50 from the US and 50 from someplace else. So it gave us a lot of actual ways that we could then start to collaborate with others, because they're looking for people that are of different diversities. And there was even a paper recently, I think in Nature, that said genomics right now is very white, right? It's very European. But we have one where we're seeing it from all over the world, and we found that we're very strong in South and Central America as well as Middle Eastern. But we, other than I think you see a lot of spots in Africa, we cover most of the world. So that was the first way we used Tableau to really promote, yeah, you really do have a diverse population. The second part of this was we started to get a lot of questions on environment. So, genetics, this at nature versus nurture. And so you only taking 25% for genetics or 30%, depending on who you talk to. Where are these people living? What environmental exposures do they have? And so we wanted to visualize that. Where are our patients coming from? So this is, you can see Washington, D.C. is right here. Our hospital is actually the epicenter. And so one of the nice things about, again, D.C. and Northern Virginia is we have a pretty dense population. And they were coming to us from mostly that area, but you can see they were sprinkled all over the place. And this is about a year ago, we wanted to look again for some collaborations. And one of the questions we have is, we have a longitudinal study. This is where they enrolled. That was when they enrolled. Where are they at now? So we've been tracking these kids now, at that time, for 3 years. So where are the families going to? Are they staying in DC? And what we found was they're not. They're moving all over the country. And that was the other thing about this is, we have longitudinal surveys that we give every 6 months. We wanted to make sure that we were tracking these people correctly. And we have actually a world one with people in Europe now. We have people all over the place. So in DC, they spread out. They don't necessarily stay all the time. And what ended up coming out of this actually was we got a grant it's called the ECHO grant. It's a very big grant with Mount Sinai and I think it's Boston Children's to watch these kids. And they really wanted to see this. Can you produce where your kids are coming from? So these types of visuals are actually helping us market ourselves to others and actually making us some really nice science, some really nice money coming in the door. Again, very easy to do this in Tableau. The other thing that's we were surprised with when we started to do the electronic health record data was, is it consistent? Where is it coming from? And one of the things that I do when we first came in is we have an event table. So think of, these are encounters, by the way. So this is the number of encounters for just our studies, and we're actually, Inova does about 1 million patients a year that come through the health system. We only have 15,000 people in our study, so this is a very small sliver of what's going on. And so this is number of encounters over time, and that's when the study started right in here. And this is, we did this as of July of 2016, and you can see there's a pretty big spike right here. And we're like, why did that happen? And again, I had only been there for 3 years, so this actually was pre me coming on board. Well, what that was is this is pre-EMR data. So what they had is they had multiple EMRs sitting everywhere, and they went to Epic. And Epic was big and monolithic, and they spent hundreds of millions of dollars on it. And what it did is it started to explode that data. And you can even see up here, it's still fairly inconsistent for us. But now we're starting to see ways that we can start to model this data in Tableau to understand what are we getting. This data is alive. I mean, it's constantly coming at us. It's not going anywhere. And when we're looking at this from more of a research, but applying that research, we want to have these feeds coming to us all the time. So a couple use cases, and I'm going to jump to the end here, because we'll get into my PC again, is to look at some of the ways we've modeled this data very quickly, just to give you a flavor. So this is all data inside our firewall, but it's all de-identified. So if we look at this, this is the electronic health record data. And again, it's very metadata driven. So a CRF name is the case report form name. And so as we add more things, we don't have to actually change the report. They just come in automatically. And what you see here is our medications form and our enrollment form. And then across the top is the people. So even as we enroll more people, this thing will dynamically shrink and contract. And we can put all kinds of parameters in here. This is more for data management for us, as we wanted to see things. So the number here is how many times did that person answer that question. And this is a medication form. So you see some people that don't do any medications. They didn't say they had any. And you see people that have 15, 10 types of medications. So the other part of this that's been interesting for us is that some people never come back to the healthcare system after they're born, and some people come all the time, right? So then you start to see more interesting use cases, and people can get alerted when they hit a certain level of they're taking this type of medication. Now, this is for forms that we predefine for them. We're also doing this with diagnosis, because we're getting enough kids now that are getting 4 and 5 years old that they're now saying, oh, you know, how many of these kids are getting autoimmune diseases? How many of these kids are getting asthma? How many of these kids are getting bigger? You know, they're obese. There's a lot of because we have a very huge, big, high Hispanic population. They seem to be the ones that are actually growing the fastest, and they're very interested in that. And then comparing against normal kids. So we're actually starting to build cohorts just on watching the data come in. Like we're not even, the hypotheses are coming to us, which is a little bit different. But we have to actualize this data back to the 20%. This is the 20%. But in this view, I just wanted to show you that this is actually one table. And let's see if I can go to the next screen here. We also do a lot of stuff with race, matching it up. So the other thing about this is that there's a lot of ways they call things in source systems. So we do a lot of data blending, which is what I'll call it. So they can call different things, and it's a way for us to visualize on the fly, you know, what types of ethnicities that we're getting into our studies. Let's see, we have different, let me go back to this one. This is a particular study. So again, we're looking at completeness of records. So sometimes people are filling in sporadic things. So we wanted to see, this is the number of questions that were answered for a particular individual. Again, the people are across the bottom. And as we wanted to find anomalies, people who didn't fill anything out or people who filled out things a lot. As you go through this is one of our studies that's been done for a while. We got to the end and we saw all this over here. And we're like, why would at the very end of the study we be having a lot of cases that they knew a lot about? Well, it's because they were closing out the study. And all of a sudden they were looking at kids that were born prematurely, and they wanted as much information about those people as possible. So all these were mothers that had premature births. And so again, we're looking for ways that we can start to make sure by the time the analyst gets the data that it's the most complete that they can have. So that's one use case. And the second use case I'll give you is one that's fairly recent. And I thought it was interesting because we have a bioinformaticist who was very interested in if the age of a person caused their, what they call mutations, so aberrations in the genomic code, is how old you are you having more and more mutations as you age? And because we have a broad population, we have mothers that are 18 and we have mothers that are 48, we have dads that are 18 and we have dads that are 65. You know, do they see trends? And she did. And she's actually going to be writing a paper in Nature about this. But for her, she's like, well, and this is just basically mother's age versus father's age and where they were represented on the screen. And she saw a mother and a father, let's see if I can find it, where they were 18 years difference. And she was just very, there's 3 of them. And she's like, I just don't think that's normal to have a mother that was 18 years younger than, or older than the father. So kind of your, there's a term for that. But she was very like, why are we getting 3 of them? So what we ended up doing is trying to analyze the data to say, why is that truly that? Because it was very important to her paper that that was right. And so we used Tableau, and within 15 minutes, we came up with this graph with some of the calculations over here. So what this shows you is how many of our mothers and fathers are the same age? And that's just, we just do birth date differences. And about 15% of our mothers are exactly the same age as dads. In this case, mostly the dads are older, right? 65% of our dads are older, and the mom's about 19.53%. But when we started to open it up a little bit, so we started to bin it, open it up, I hit it twice. We started to see that, yeah, a little bit more, and here's the one she was really concentrating on. But if you open up even further, you can see that the distribution is pretty normal. I mean, we didn't see any aberrations. But when you looked at this last one, so we looked at this mother, and again, this is all de-identified. Let's see if I can find the details here. What we found was, oops, I guess my skills aren't good today, is that when you looked at the dads in this, I must have just done one, it's 18 and 19, sorry. Let me go back to the review. I want to get all three of them to show you what she found. Yeah, there's three there now. Maybe I get some Tableau training on how to hit this right. What we found was, now these are our internal IDs of how they are. So they are three different distinct moms. But if you look at the dad's date of birth, and we do date of birth, we blend it, meaning we look at the date of the baby and say, how old are you in days? We found out it was the same dad, same mom too. And so what ends up happening is that these people were actually re-enrolling over and over again because our studies were so long. Again, something we didn't anticipate when we first got into the study is that these moms wanted to know about their babies. So this mom had come in 3 times. She was 38, 39 years old, had found a 20-year-old man, and in 3 years, she popped out 3, right? So it changed the way we did the analysis. It changed the way we did the graphs. And it also changed the way we look at things operationally. Now we have data that says you're what we call dual enrollment because we don't want to sequence you again. It's going to cost us $2,000 to sequence you. So what did this actually end up doing is saving us hundreds of thousands of dollars because now we don't have to resequence the mother and the father because they're the same. Now we still get blood on them because we want to look at methylation and other types of epigenetics, but we don't sequence them. So this is actually something that was good for her paper as well as it saved us a lot of money. So those are 2 kind of interactivities that we've had. And again, we did those in 20 minutes, 30 minutes. It wasn't like it took us a long time. So moving forward, we're also doing a lot of clinical testing at Inova. So what this has proven to us is that it actually has impacted our families. So what this is a little bit of different look. So what Inova has done is that they've offered to sequence infants at birth for pharmacogenomics for every infant that comes into that hospital. And we do about 10,000 births in our main hospital. And they do this for free. And the mother has to consent. We don't do it without her knowledge. She has to do that. But what this is, and let me see if go back here. What this is this is the genes. So we're looking at certain genes, FDA approved genes for pharmacogenomics. And then this is the nationalities across the top. And what you're seeing here is the variation within those genes. So how many different alleles do we have? And so what we're seeing is a lot of, obviously, stratification. And it's one of the areas of opportunity that we see as far as we're now having 4,000 to 5,000 kids. And it's going to be yearly to start to look at this data. So we get, obviously, the calls. We have a company out in California that does the actual annotation and the reporting, which is its own conference. But we're seeing a lot of variation very quickly. Again, in Tableau, I want to say this one took like 5 minutes because the data is not that big. This is HL7 messages that we have a parser that shoves it in here, and then we can connect it to any health record data you want. So when the molecular biologists saw this, we're like, holy crap, right? So we're in the automation stage. So that's just back to, you can't automate everything. You have to automate the things that are important. And so by doing this and investing a half hour with that team, that cross-functional team in a room, we're able to target the things they really want and automate that. So that's all fine and dandy. That's the data side, but the infrastructure is not trivial either. So I'll move through this pretty quickly. But what we've had to do is actually build a hybrid cloud. And that's because the health system wasn't ready for this data size. Health systems, they're pretty tried and true. They want a capital expenditure and they want you to do this, this, and this. And when you get in a research environment and they go, how big do you want it? And they're like, I have no idea. As big as we can get it, right? So what we've had to do is, this is the evolution. So the bubbles here represent different networks that we've had to build or broker. So everything kind of started down in the Inova side. So this is your Epic, this is your laboratory systems. And then we've separated our Amazon. AWS is Amazon Web Services. We were one of the first people in the country to sign a BAA with them. We didn't know that when we were talking to them. We thought everything was great, but then we found out we were one of the first ones. But it took us a year. Again, health systems are risk averse. But we have various rules we have to adhere to. And then we created our own research network. Inova wasn't a big research place. We weren't at an academic health center, so we actually had to isolate ourselves because, again, big things break, and we can't break what they're doing. So that's the big picture. The first things we did with Tableau for the big data is we started to look at the genomes themselves. So we had started sequencing in 2012 with a company called Complete Genomics. They don't exist anymore. They were bought by Beijing. They don't service America anymore. So after the first study, no more Complete Genomics. And it moved to Illumina. So what this graph shows you is the file sizes. So genomics, by the way, are not just one file, they're many files, packages that they send us. And then across the top, well, that's the count of files across the bottom. This is the size in gigabytes. And what you see is, this is probably why Illumina is pretty good, is because Illumina is very consistent. Very consistent. Whereas Complete Genomics, look at that. And they're huge. So they're 3 times the size of Illumina genomes. And so we were getting files of 350, 450. We had to account for all those. Like, where are they at? What's happening? And the reason is because they did it by chromosome. Good for them. But you can see how it's pretty messy. And actually, the first thing we saw was this. Like, why is this such a 2 different things? It's because they gave it to us twice. We didn't know it. So they actually upload their data right to our Amazon, and we account for it every night. And so what we found was they deposited a bunch of them twice. So again, saved us a lot of money because in Amazon you pay as you go. Like, so it doesn't matter, every month we're getting charged double for those genomes. So again, this saved us probably thousands of dollars over the life of our studies and probably more. So then the other thing about what's going on now with Inova, and I think with a lot of people, is like, how big is this going to get? So we're managing about 5 petabytes of data across those 2 environments. So a lot of it's source data that just gets replicated. So again, you become this data hoarding mechanism of data everywhere. So this is what a size, again, this is a Tableau representation up here of typical data package that we get now is about 140 gigs from Illumina. We don't get the raw data. We get they call fast queues, BAMs, and variant files. But this is what our data looks like, and this is actually a little old. We probably have closer to 9,000 that have been fully vetted. So it's about a 1.1 petabyte. And again, this is based on Illumina metrics. Because we had about 3,000 complete genomics, this is actually numbers around 2 petabytes. But again, what you're seeing here is actually what I'm pitching to my health system. So you get a little bit of inside information on what we're trying to do. But now, when you look at, hey, let's do the patient population, that's at 8,000. And actually, there is one in there. You can't see it, but there's actually one genome wedged in there. But that, if we did our patient population, we're going to sit at about 134 petabytes, and that's just data sitting there. That's not doing anything. And that's not cancer. So cancer, a lot of times you'll sequence 1 or more, the germline and the somatic. So that's just if you brought everybody in and did it. Now, a cell system isn't going to support 134 petabytes, right? But they wanted to know if we were going to do that, what it would cost you. And so we can put metrics in AWS and tell them exactly what it would cost. And they weren't happy with that. So opportunity-wise, what does that mean? So what do we think, what have we been doing? So we talked a lot about the model, we talked about the management. In a hybrid cloud, you kind of can pick and choose where data might lie and what you compute off of. And there are 2 different models. Either you have the capital expenditure where you buy and you're going to, regardless of user or not, you're going to pay for it one time, or Amazon's pay as you go, right? So what we did is a bunch of experimenting, and again, a visualization in Tableau of running our, these are the patients across the top, and we ran different types of quality control against the binary files. And so we experimented with data that was all in the cloud. So think, for those of you in the cloud, think object store. We would point our compute, elastic compute against it and do the QC. A hybrid cloud is where the data would sit on Amazon, but the compute would be on-premise compute, so hardened physical boxes. And then the on-premise was, we have an SGI UV2000, so huge in-memory machine, 16 terabytes of RAM, a petabyte of storage, high output. I mean, it's a monster. But in genomics, they don't use that right. They don't use the parallelization of the way you can do genomics. So what you see is the all cloud is better, and the reason is because number 1, it's co-located. Number 2 is you can spin them out, you can do multiple clusters, and the bioinformatics and staff had found ways to parallelize this more efficiently. The hybrid cloud was actually pretty good in the middle of that. And the reason the on-premise is that bad is because number one, the algorithms don't work for that machine that well. And number two, we want to do this in real life. And when you run on a shared machine, you're sharing resources. You might be in the queue with someone else. In Amazon, that's not a problem. Amazon just says, spin them up and go. So, but again, there's cost differences here. We were exploring what would this look like. If you want to go to 10,000, 100,000 genomes, what is the model for that? So we did a lot of analysis to give them numbers. So what this ends up becoming is more of a hot tiered storage. So again, these are that same 4 bubbles. And what you'll see is, we might get, I'll start down here at the bottom, and you're going to watch this kind of light up, is that we end up having this data kind of deposited, and we've created the automated pipelines, and this is very common in bioinformatics. And the darker it gets, the hotter it gets, meaning it's put on faster storage. It's now, think about it as a funnel. So that 2 petabytes now is getting winnowed down into what the analysts truly like. And then the other thing that we had to do is that just because you have big storage up in Amazon and you have nice compute on-prem, how do they connect to each other? So what we end up finding is the network is always going to be the bottleneck. And the network is different based on the type of data you want to move. And I'm not a networking expert, so we had to go outside. And we ended up getting a direct connect through Amazon. The nice thing about DC is its Department of Defense has built that area up. So bandwidth, it's just what do you want to pay? So we have a direct connect between the two of us that is dedicated to us. So we can download pretty fast. But we still don't do it because you still get costs. There's a cost associated with download. Amazon will let you throw it up there. Hell yeah. But they don't want you, they're going to charge you for every little nickel and dime. So again, another cost pattern that you'd have to worry about. But then once we got it down, again, a very smaller size, we put that into these compute environments. And now I'm going to go down to the bottom over here. We do that within our clinical network. So what you saw was this ETL. We use SSIS, Microsoft, because that's what they use. So no cost to us. We just kind of piggybacked on them. And we move that through in that model that you saw. So all that data gets manufactured, and this has been running for about 3 years now. It's the first thing I did when I got there. And then we move that into the research area, de-identified and modeled. So then in the middle, now the analysts have one place to go. And they can actually spin up resources up in Amazon and look at the on-prem because we have the dedicated connection, or they can be down here and they can be looking up data up here. And the other side effect of this is that when we want to collaborate, the data is already in Amazon for us to collaborate, and we control that with our compliance with the BAA. So just because I do this for the executives, because sometimes you get the cookie cutter stuff and they're like, what does that really mean? So I'm an accountant by trade, and so we have cost accounted every single step. Because number one, it would drive me crazy if I didn't know how much something cost, and when we were first building it, we had no idea. We just got a bill at the end of the month, and it was huge. So now we're going through the budgeting process, and these are individual lines. And I have another graph, because then we broke this down into the pipelines to know each individual step. So there's logs going places. There's all kinds of craziness. I won't bore you with the details, but this has evolved. This is not what it started with, not even close. It was one bubble, and it was probably a huge, massive bubble. So to end up today, what do we think is next for us? Because we've gone through a lot of pain. This took a lot of pain to get through. Again, this is what I show the executives. They want to latch on to something. They want to say, what is it you're doing? Why do I have this big bill? And we want to become a data manufacturer. And a lot of you are probably already doing this. Again, this is just to conceptualize what this is. So we want to take that crude data down here, and we want to start to collect it to learn, enrich, and improve it. And so those pipelines you saw with the big things, that's all we're doing, is we're just moving crude data through to actual actions that you can take. So that's what we've been trying to build. And again, another funny visual is really, we don't think that we're also going to be biomedical as well. We're looking at sensors. We're looking at whether they're in the hospital system, in the operating room with the NICU babies, whether they're, if you've seen the stuff from Under Armour, where they're actually embedding sensors into you so you can start to do sweat and analysis. We're a research environment, so they want these types of things. And again, we can isolate them and say, we'll just do that as a one-off. But if you really, truly want to utilize that data, why don't we become a manufacturer of it? So if you don't want it, we can throw it into cold storage and it's done. But if you want to actually then start to bring that back, so at the very end, we want to start combining data for the different use cases that we're getting, because we're getting a lot of use cases, that we can have a tried and true way to organize that data to allow people to actually use it. And then this is the last slide, or second to last slide. we actually had to visualize what this meant, and so we're in the process right now of building our biological processes. So all this actually already exists. What we're doing now is we're automating it in Amazon and getting the most efficient use out of elastic compute, long-term storage, and then I think the last one I'll show you is that we built a Hadoop cluster up in Amazon for that variant data, for our annotations, and for our clinical data, but Amazon was super expensive to do that. Amazon's still expensive for compute if you don't use spot instances and all the quirks that you can do to lower your costs, and we can't because we can't have shared instances. So what we ended up doing, and when hopefully when I get back to Washington and Virginia, we set up an on-premise compute Hadoop cluster with Cloudera and with Cisco that was customized for us, high memory, because what we're using is Impala, which is SQL on Hadoop. So we did some testing because, again, we didn't think SQL Server, we didn't think Oracle were going to hold what we were going to have. And so what we ended up doing is piloting with a company, also with the Institute for Systems Biology, which is out in Seattle, so a hometown of Tableau, to build this. So they were the bioinformatics people. They were a TCGA partner as well. And so this is just a real simple statement anybody here could write. And this is the variant file. So this is all the variations of me and you and all our patients in a file. The sample ID obviously is the sample, so everything's based on a sample that I took for myself. And then we just did a count. So the first thing we wanted to do is just, hey, let's look at, can we run these queries? Now, what we saw was, again, back to our complete genomics in Illumina, when we looked at Illumina, and we go for the whole genome here, it's about 37 million per sample. And you can see complete genomics is about 22 million. You're like, well, that's 39% difference. And some of these cases are exactly the same people, same blood sample. And there's been papers written about this. Most of it's just semantics. There's this thing called no calls, where the machine wasn't good enough to make a call. Illumina treats them differently than complete genomics, but you have to know that if you're going to combine the data sets. And so we really quickly with these queries could visualize that, and it was taking our informaticists weeks to do. Now we were doing it with just a really quick SQL statement. And then when we looked at, hey, what is this going to look like across all our genomes, we did the math, and I'll skip to the end here. As far as data point wise, we're about 7 trillion data points in our system, and that's for 8,275. Again, think about that number when you're doing 1 million of them. So this on-premise cluster that we're building, we can return results in seconds against that. And we've actually tested Tableau against it, and then we use Redshift, which is a columnar data store in Amazon, because they were both in Amazon, and we were doing blending to see what it would look like, and it worked. Now, again, it wasn't optimized, but that's what we're going to be doing, is we're going to try to find the right tools to layer on top of this more traditional SQL type of look. Now, all data isn't going to look like this. I mean, some of it's isn't as linear as genomics is. But it was a nice proof of concept for us that now this on-premise cluster will break us even in about 7 months, because now we're not spending that money every single month on Amazon. So the cost models have changed quite a bit since when I started into research about 9 years ago. So, and then just for data size-wise, that's about 12.5 terabytes. Now in Hadoop, you have to store that 3 times, because that's one of the things about Hadoop. It's supposed to be resilient. If you lose a node, it'll auto-replicate for you. And I'll tell you, on our SGI, if you break something, it goes down. It is like a Formula One car, all right? You got to tune that thing. Hadoop's a lot more resilient for us. But that's sourced from about a 1.75 source data from whole genome sequencing. So again, back to the accounting in us, we can now have a nice metric that says, well, if you want to do another 10,000, this is what it's going to cost you. Here's how we're going to manufacture it. And it's something they just didn't have. So really, to summarize today with my last slide, translational research, there's a lot of varied informational challenges that we've had to overcome. And hopefully I've given you a little journey on some of the things that we've had to, but there's many more than this. It's still expensive. It's not for the faint of heart. It's not something you can do on a weekend. You really have to make it a concerted effort if you or your company is going to do this. And we've spent, I can't even tell you how many millions of dollars in infrastructure. Data management, what we found is the data management and analytics, sometimes they separate in people's minds, but we're trying to build a team that can blend that together. So when you think of just pure infrastructure, IT, traditional IT, you think of data science and the analytic component, and then you think of business, because again, this has got to be a business. What we're trying to do is really harmonize those 3 things into a team that can support all the use cases that they're throwing at us. But there's always going to be trade-offs between quality, speed, and cost. We don't want to sacrifice on quality, so ours are usually how fast do you want it, or how much we're going to pay for it. And again, we didn't have that metric until recently. Maturity of the processes. So where we've been interacting with people on the self-serve analytics side is really on the operational side. So they like their dashboards. They like to see how many patients are coming, how they're doing. Our research and clinical laboratories like it because they can see their shipments. They can now see some of the data coming back, again, from those analytic costs. Bioinformatics is just starting to get into this. So that's one of the things that they are just starting to see the relevance here, especially when you can do this thing so quickly. Now they're using a lot of R, a lot of Python, a lot of custom in-house open source stuff. But now they're seeing this, and there's an ecosystem building around this. So for those of you who, Cal Berkeley has a thing called Atom. Mount Sinai and us have been working a lot together on building this into other even Hadoop tools, because Hadoop just isn't one thing. There's HBase, there's a new one called Kudu, and so we're trying to work with them on a pipeline of how this would work. And then data infrastructure and management is what you saw mostly today, which is where I'm trying to help our administration understand why we ask for so much. Self-service analytics, we're looking for ways to scale that, because a lot of times now they come to us and we have to build the report. Now what we want to do is just really democratize that data to others, and they're just starting to grab hold of it because they see the ease of use. And then lastly, Tableau has helped us, and so whether it was the quality of the data, whether it was lowering costs, whether it was, again, back to this democratization of data, this has been a key tool for us to really realize the potential that we might have as we move forward. So I will end it there. I made it.
We have about 10 minutes for questions. We'll take a few questions from the audience. Please go ahead.
So
Can you repeat the question?
Yeah, so is there a place for metadata standards? And right now there is, but it's very manual procurement. And so we are looking for tools, if anybody knows of any, that could do that across an enterprise. There's various things there. There's another one for data cataloging. So again, some of this data we can't even model yet because we haven't seen it, but we want to know where it is and we want to know who gave it to us. So think about that hoarding. So finding tools that can do that and not having one tool for every little individual use case, because then it's not harmonized. So Hadoop has some things that are on top of it. We've been evaluating those, but for right now, we've been using what I would call data dictionary tables that blend our data together, and we use that, and then we have wiki pages that help people interact with it, but we don't have a real slick tool for that right now.
Question back there.
Yeah, so the question there is, it's been discussed. There's not an actual plan to do that, but we actually collect longitudinally more samples. So we do microbiome now. One of the studies we're going to do is actually on teeth. So Mount Sinai in New York City does some really cool things on teeth. So the protocols are built to continue to collect, so we do find a reason to do that. We will absolutely do that. But right now, we do collect take that back. We collect blood on mother twice. We collect it on when she's about 15 to 18 weeks before she's given birth, and then we collect it at birth. We do that more for expression than for genomics, but they have done a couple of them, again, more for just to see is that still a valid truth, that nothing has changed. And we have partners who are, like I said, interested in that. We have not done anything like that.
Any other questions?
I'm sure you guys get a massive amount of Excel files. What parsing do you use?
So the health system does most of that for us. We have done stuff. There's an open source tool that one of our bioinformatics did. If you can, I can email it to you. I don't have it off the top of my head. It's a nice GitHub repository. It's HL7. Does kind of continue to evolve, and there's a lot of FHIR standards that are coming in that we're interested in seeing for genomics. So I'm on a steering committee in the state of Virginia. I work with the National Laboratory of Medicine on standards. So they're very novice right now to genomics, but for some of the stuff that we're working on, yeah, we have a generic parser that, because that's all pipe delimited. If you use the old version, I think the new version might be XML. But yeah, we've found a nice open source repository that can help us with that. Yes. Yeah, so I'm also on the genomics working group for EPIC. The issue there is, at least for us, we're always 2 versions behind because it's hard. They have a cycle every 2 years they'll update. So I think the new 2016 of EPIC, they have a genomics module, and I say that in quotes because it's like open source text. So we're working again on the HL7. Like, we want the discrete results. Like, part of this is we want to get the most value out of that data. We're going to spend a lot of money to generate it. How do we put it in a place that we can do clinical decision support? We can do other types of studies within the EMR. So when a baby comes in and we did that sequencing and they try to give them coding, the doctor gets an alert that says, hey, you know, you might want to change the way you treat that baby. Right now it's a PDF report, and we did like 6 iterations of that because doctors are so busy, they don't want to look at 27 pages. And I've had mine done. By the way, it changed the way that they treated my dad because I was not a good responder for Plavix. And this summer he had a 99% blockage in one of his arteries, and they took him through and they were going to give him Plavix. And it's 50-50, maybe we would or wouldn't, but we didn't want to take the chance. So it's impacting me personally, but you know, the way we want to do this, what the utility out of that data, right? So yeah, these are very problems that we're thinking about quite a bit. Thank you.
I think there's a question back there. Yeah.
What was your methodology to standardize upgrading your data models, especially on the oncology side?
We don't do a lot of, well, on the oncology side for TCGA, we had what they call disease working groups. So like, was it melanoma, if it was kidney, whatever, they had many calls to standardize what that model would look like. So for cancer, they might have 25 to 30 variables that were always the same, so stage, all kinds of things that were vetted. But then for every single different disease, they had different forms that were specific to that. So again, we did it very metadata driven, and what we used OpenClinica, which is a CRF for the data collection. Metadata Rave is another one that we use. And the way they store that data actually is very metadata, so it's very easy to translate. And then we registered everything with the cancer registry. So there's the National Cancer Institute has a CDE, Common Data Element. I don't know if it still exists actually because they just rebranded themselves. But we registered every single question and all the elements into that repository, and that hook, it was this a randomly generated number the NCI gave you, was part of the data dictionary. So those were all hardened, but they were constantly changing, and so it was a pain in the butt. But right now at Inova, we don't do that much cancer, so we haven't had to broker that yet, but it will come.
So with the large quantity of data that you manage, how do you, like, what stat tools do you use to QC all the information and ensure there's data integrity that's going through the pipeline?
So it depends on what it is. So for example, in genomics, we have, think of 3 layers of QC, and it's all either open source bioinformatic tools that have been hardened by, you know, various institutions that are kind of best practice. So when it gets into Amazon, we'll do MD5 checks, we'll do structural checks. Do we get all the data? Is it a traditional size, which is why that sizing made sense. So if we get a size, a file, even though the MD5 said it was okay, it's twice the size, we're gonna question that. So then that's all logged to a place that we can then query off of. Then on bioinformatics, they'll do things with, they call them hem-hat ratios and TVA, and all these types of statistical analysis on, is that a human, do we have all chromosomes? That is all automated as well. And just for an example, we did 8,000 for about $1,800 in Amazon because you can spin them up and shut them down. And it's just a plug into that pipeline. You just point to the bucket and it goes. And then the third one is back to the nitty gritty. Did we sequence that person before? We don't want them in our database if we did it twice. Is the family, so is the dad really the dad? Right, so the reason that most of our patients don't consent is the dad gets cold feet at the end. No, he doesn't say it's because I don't think I'm the dad. He'll say it's because I'm afraid of needles. But that's the main reason to do that. The other thing would be, are they part of the family? So we do all kinds of ratios of, back to that, the map you saw. We have done reference genomes to know they actually belong in Southeast Asia. So we don't self-reported, we've also found people don't self-report their ethnicity very well. They don't really, it's more to the skin color than it is to what their biology says. And so there's all kinds of analysis to say, yeah, you said you were mixed race, but you're actually, not, for lack of a better term. So yeah, very interesting things that we try to do as and then in the pipeline you plug it in, but then the problem is that worth our time, right? Is it something that just is so exhaustive we're never going to get the value out of it, or is it something that we just plug right in, it's an extra 5 minutes on the QC and we move on with life.
So you're hoping on
So we're an honest broker. So we have the MRN as it comes out of the HR, and then we have a separate database. That's all it is. It's just that mapping. So if we want to do that, that's a special request from the principal investigator to say, yeah, I do have some kind of incidental findings. The patient consented to know them, because the patient can say, no, I don't want to know, right? So, and then the whole, what is an incidental finding versus what's actionable is something that a lot of ethicists are talking about. But we very much define them for them, what we would tell them, what we don't. So honest broker is the answer to that.
Any other questions? Back there.
An opinion. I don't necessarily have an opinion. I would just want someone to choose. Again, the healthcare is like a standard of standards, right? And so HL7's been always done to exchange the data, not necessarily just you store it as documents. Where the CDISC, I don't have that much. I haven't done much with CDISC. So there's another one called OMOP that we've done a lot with. So again, it depends on what your use case is, and is it extendable to genomics, right? So for us, we've been more interactive with HL7 and LOINC, which is the laboratory coding. So we've been sitting in with the National Laboratory of Medicine, who are actually, I think in the fall, they came out with another standards, whatever. And if you get that in front of 5 people, they're going to have 5 different opinions on whether they like it or not, which is why it's very difficult. And what we've chosen to do is make it interpretable for us. So if we understand it, then we can translate it to whoever wins in that given scenario. But if you're trying to go to some standard that you don't understand or don't like, going to another standard that you don't understand or don't like, it just complicates it quite a bit more. So I don't have a good answer for you other than it's probably why I have no hair, right?
So I have a question. 23andMe can do a genomic profile for $199, right? Veritas can do it for $1,000. So based off our interaction, I just wrote this blog post on how will precision medicine enable population health.
Yeah.
And the central hypothesis that someday you capture the genomic profile at birth, and that really becomes the basis for the personal health profile going forward. So how far are we away? I mean, you guys are pioneering it. So how far are we away from seeing this?
It's going to be
proliferate?
economics, honestly.
Yeah.
Economics, and what's the political kind of overtones on what you can do, and how is that going to hinder places that are pushing the envelope? That's why 23andMe got a little slapped, because they were pushing the envelope. And back to the direct consumer, people are demanding this stuff. So if you're going to make a lot of money on it, why are they? So it's putting a lot of pressure on places like us. They're like, why won't we do it? We got the talent, we got that, but there has to be a business model, and in a health system, they're not built for direct to consumer. Right? How do you pay for it? And just kind of anecdotally, I was with my relatives. They're from Texas, and we went out down the street, and they had done Ancestry.com, and my uncle had gone and done it 3 times, and they never could give him results back. Like they couldn't do it. He was half American Indian, and they just, for some reason, couldn't pick that up. So there's some very interesting caveats to what people are doing now. We're very interested on the ethnicity side just because we have so much of it. But yeah, it's a very interesting time for, and there's a lot of philanthropy going into this now. So all these announcements on, Sean Parker and Facebook and those types of people coming into this. So it's going to be a very interesting time on how this all works, people pushing the envelope versus what's medically relevant.
Yeah, the big picture cost-benefit analysis, or the trade-off is that incremental $1,000 you invest up front will pay 10x to 100x over.
Right, but how you prove it?
Yeah.
Right? So
We're not there yet.
Yeah, that's the other part of this is that you do this.
It's the preventive.
Well, Inova's eating $300 a baby right now. So how do you prove that that's going to save X amount of dollars over time, and then prove that to Medicare or Medicaid or whoever, private insurances? And so there's actually a lot of movement now for bigger companies to do their own insurance, and then they'll pay for a sequence because they think it'll better treat them. So there's a lot of people that are kind of switching around, and we're seeing a lot of it in Washington because there's a lot of discussion about this with the FDA and how this is all going to play out. So it's, like I said, next 4 years are going to tell us a lot, I think.
Okay. Scott.
When I saw that, I was actually wanting to try it to see what that would do for us. There's always ways to speed things up, but what is the right thing within our ecosystem? So we'd love to pilot something like that to see how that would work. because the faster we can interact with our scientists and our clinicians, the better we're going to be.
Awesome. No more questions? Okay. Thank you, Aaron.
Thank you very much.
As always, a pleasure. And thank you very much. Please feed in your feedback in the TC16 app, and thank you so very much. Safe travels, and see you at TC17.
Yeah, all right.